And welcome everybody to today's webcast. Appreciate you spending a little bit of time with us well, whether it's this afternoon or this morning, not sure where you are throughout the country, but your time is very much appreciated. I think you'll find this a very interesting webcast, covering some really cool stuff, some really cool technology. Again, I'm Carl Smith with the Manufacturing Technical Services and Professional Services team. Joining us is my colleague Ed Gilman, who is a specialist with finite element analysis, as well as CAM, as well as, I don't know, probably rocket scientists, everything else. So we'll welcome Ed with us too. Just a little bit about us before we get things kicked off is you know, if you're not familiar with Imagine and who we are certainly one of the industry leaders in expertise and services around design management, design software and its management. We have particular processes and proven workflows to help you guys get optimized and more productive with whatever technology you happen to be using. Imagine it is part of RAND Worldwide, an umbrella company that includes us, a company called RAND 3D, and Ascent. Ascent is our courseware. If you buy courseware for Autodesk and other CAD systems, you're going to get it as published from Ascent. And of course, RAND 3D is our sister company that deals with some other types of engineering software. So expertise in our world all over the place. Here's a little pushpin map. It gets updated all the time. We're certainly in a growth mode and bringing people on board to further assist our customers all over North America. I like to look at this map and reiterate the fact that even though you may have a local pushpin wherever you might be in this map right here, look at all of the others all around it and feel rest assured that if somebody can't figure something out locally, we have all kinds of folks in all kinds of situations to find some details or to find some further expertise or better workflows. Somebody somewhere has seen something that'll become of use. So if you're ready to take a look at the presentation, I am ready to pass the presentation over to Ed, who will spend the next, I don't know, half hour, 45 minutes with you discussing Nastran in CAD. Ed, you have the con, sir.
All right, thank you, Carl. So we'll go ahead and get started with my portion of the presentation here. So I'll go ahead and share my screen and we can get started with Nastran in CAD, just taking a quick look, as well as looking at fatigue analysis and what we can do with that. All right, so I'm going to be talking about Nastran in CAD, and I'm focusing on the 2019 version. So if you're using an older version, some of this may be new to you, or you might not have seen it before. And so we'll go ahead and get started. So in general, I get questions a lot about, you know, why should I consider using Nastran in CAD if I already have Inventor's stress analysis module or Inventor FEA available to me? Well, you may find that Nastran in CAD has a lot more capabilities. So even when it comes to just things like meshing, we have the ability to add in individual part mesh. We can do mesh quality checks. We have the ability to look at our results based on element types. We can use a combination of our basic solid elements. We can use shell elements, line elements, and we can combine all of those to really get a nice simplified model that gets us the results that we need from our FEA. We also have the ability to now, basically since 2017, now with Nastran in CAD, you can access the solver separately from Nastran in CAD. So if you want to work directly in the Nastran solver or make changes in the background, you can do that. So you have a lot more control over the solver itself than you would with any other software. When it comes to analysis types, sometimes you only need linear static analysis. So assuming that displacements are small, assuming that our load remains constant in its magnitude and orientation, we can make those assumptions, but sometimes we need to look at our designs in a more dynamic way. So we can run modal analysis, but with Nastran in CAD, we can also run vibrations. We can look at frequency analysis. We can run transient, so we can apply our load to be time dependent. Shock response spectrum, fatigue analysis, which we'll talk about today. There's a lot more options we have with Nastran in CAD, so we can evaluate our products in the most efficient manner possible and get the results that are really important for optimizing our designs and reducing costs. So some images of what we can do with Nastran CAD. You know, we have the basics, our linear statics. We have modal analysis. So what are the natural frequencies of our components in our assemblies? But then nonlinearity we have with Nastran CAD as well. So we can do some impact and drop tests. So looking at time steps and time-dependent response, as well as looking at deformation. So maybe our component isn't actually going to fail. Maybe we'll see some yielding, we'll see some deformation, but we won't see true failure, and we won't see the material reach its ultimate tensile strength. If that's the case, we can only evaluate that type of deformation with a nonlinear analysis. A linear static analysis won't get us that data, and so we'll need a tool like Nastran CAD to get that type of analysis. Also, advanced linear dynamics. So if you want to run shock and vibration, you want to run shock response spectrum or random response analysis, these more complex analysis types are also available with Nastran CAD. And then additionally, just to note, you know, we have buckling, there's fatigue, which I'm going to focus on today, thermal analysis, and then just an array of more advanced settings using connectors, element mixing, concentrated mass, etc. So there's a lot more that we can do with Nastran CAD that we wouldn't with a basic analysis software. So let's talk about fatigue. Sometimes we'll be looking at a design and maybe under our maximum load condition, everything looks fine. Our overall stress and displacement and safety factor results are showing values that we're comfortable with. We're not expecting to see any yielding or any damage as a result of our max load condition. But sometimes our designs are not going to be loaded at the max load condition in a static manner. We may see constant cycles being applied where the load, maybe a smaller magnitude, so maybe not even the maximum load, might be applied over and over and over again in a fashion that would cause damage, and this is called fatigue. So what we're looking at is how many cycles we can expect to achieve with our design before we start to see damage and failure as a result of fatigue. So we'll need to apply our material data specific to this analysis, and we'll also have to apply our load in a fashion that is dependent on time or is loaded in a way that applies the load or applies a load and then reverses the load to indicate tension and compression. So there's a lot more things we need to consider with fatigue, but this gives us really some great insight into, you know, whether or not our part is actually going to break at a lower stress level than our maximum loading would suggest, due to the increased number of cycles and the constant wear that's caused by this type of dynamic movement. So there's a lot of good applications for this, and this is what we're going to focus on today. So some of the things that we need to actually set this up in Nastran CAD, I'm going to quickly go over. The first thing we'll have to do is apply an SN curve for our material that we'll be using for this analysis. So whatever component you're running this analysis on, make sure the material specification has the fatigue data applied to it. So this is called an SN curve. We're looking at our stress versus number of cycles. So how the basically stress or basically our strength of our material changes as the number of cycles increase. So, you know, maybe after 10 to 100 cycles, we're not going to see a huge decrease in our overall stress. But when we start talking about getting to 100,000 cycles, 200,000, 1 million cycles, the actual stress of the material and the maximum stress that it can handle will start to degrade, and this will follow this SN curve. This is created through basically a series of tests to build this data. Typically, the most important region for fatigue analysis and the region that we will focus on is this elastic region, which is also known as high cycle fatigue. So what we're looking at is maybe a smaller load, maybe not quite the maximum load, but a high number of cycles. Another thing to note is if you're looking for your material data, you may see a difference in the SN curves and how they look based on the material that you're looking at. So typically steels will actually see sort of a flat region once it reaches its endurance limit. And this represents a stress value that if your part is loaded and has a maximum stress value below that line, your part should have infinite life. So your part will live on forever. It can be used for as many cycles as you want. because the overall loading condition is so low. But if you're seeing a higher stress being applied constantly over and over again during these cycles, and you're above that line, that's where you start to see damage as a result of fatigue. Materials like aluminum, you won't see a flat section after that endurance limit. It sort of just starts to flatten out at a gradual rate. So you'll sort of see this constant curve with an aluminum, whereas a steel, you'll have this abrupt switch from the curve having sort of a slope to it to being almost flat. So keep in mind, SN curves may be different for each material. Another thing that we'll need to define, and this will affect which SN curve we use and the way that we apply our data, is this stress ratio. So this will be defined as R. If we're going to be applying our load in one direction and then removing it, so this would be considered unidirectional stress or unidirectional bending, our R value will equal 0. So we'll look at the curve, the SN curve that was created under this load condition. If we're going to be applying the load in a way that would sort of rock back and forth or apply two-directional loading where we'll see tension and then compression, so load will be applied in one direction and back the other, the ratio of the minimum stress to the maximum stress applied will equal 1. And so in this case, we'd be applying basically what's called a fully reversed condition. So depending on what type of loading we're expecting on our part, we'll want to select the SN curve that matches the stress ratio that we're going to be loading it with. Another thing we'll see within Nastran NCAD is this B and B sub E value. These values represent the slope of the SN curve. So we need to calculate this for Nastran NCAD. And so typically, these values aren't just out there. You can't just Google what is the B value for aluminum 6061. You probably won't get good results. What you'll need to do is find a good resource for these SN curves. So find a good material spec that you like to use. Maybe the same material spec that you use for your nonlinear data curves. You can probably use the same one for your fatigue curves. So find some good references, and then you'll just need to calculate your B from the values that you're using. So figure out which curve you'd like to use with the stress ratio. So if it's 0 or 1 or 0.5, select that curve, and then you can calculate your slope just by taking the log of your max stress minus the log of your min stress, and then the log of your highest number of cycles minus the log of your lowest number of cycles. This will give you an approximate B value, so you're sort of just approximating the slope of that line, and that's how Nastran NCAD will interpret this SN data. So gather some data points, calculate your B value. You can do the same for BE, which is basically the slope after the endurance limit. For steel, you can put in a value as close to 0 as possible. It just can't be 0. So now that we've kind of gone through how we get this data, what do we actually need to do to set up an analysis or a fatigue analysis in Nastran NCAD? So it's 4 steps is the way that I break it down. So first things first, change your analysis type to multi-axial fatigue. Pretty straightforward. You can also do vibrational fatigue, which I'm not going to talk about today, but the option is there to do vibrational fatigue as well. Second step is just going to be defining our SN curve. So we'll take the SN data that we've gathered, the B values, all of that data we'll input in to our material spec. So we'll actually edit the material in Nastran NCAD and then define the SN curve for that material. The nice thing is then this will be saved with that material, so if we need to use this in a different analysis, we can pull that same material and it'll have that SN curve defined already. The fatigue setup is pretty straightforward. You don't necessarily need to change anything for the fatigue setup. It just does allow us to change a few settings related to how we're applying the load and in general how we're going to be interpreting this analysis. Another thing that's really important is our force. So the way that we apply our load, whether it's a load or a pressure or a moment, we'll need to apply a load time history table. So for each load, we'll need to apply it in a way that matches our stress ratio. So is it going to be applied where it's loaded and then unloaded, or will it be loaded in tension and loaded in compression as well? So we'll need to apply a load time history table that matches the stress ratio that we're going to be using. So today I'm going to do a quick little study on a real-life design that I think everyone has seen before. If you've ridden a bike, you've seen one of these. So a bicycle crank arm is just the way that the load from our foot as we push on the pedal is applied to the crank that drives the gear and the chain. So in this type of design, if we were just to look at this with a maximum linear static load, so maybe our max load condition, if we were just standing on it, that may not really be sufficient. You know, we want to know, well, this thing is going to be constantly loaded over and over again as someone goes on a bike ride. And so it's really a dynamic environment that will require some level of fatigue analysis. So the things we're trying to gather here is, are we going to be seeing a significant amount of fatigue damage? So at what number of cycles will we see fatigue occur? And where can we expect to see some damage or failure? And then we can sort of take that data for cycles and determine, well, how many miles or how many cycles can I expect my actual crank arm to last for before I see any sort of damage or potential failure. And from that, we can then decide, well, is this okay? Do we meet our design criteria? Or do we need to go back and make some design changes to improve the overall life of our design? So some basic assumptions that I've made. I kind of built this CAD model of a simple crank arm and pedal. We're going to be doing this with aluminum 6061 T6, pretty basic aluminum that is typically used for these types of designs. Obviously, if you have a really expensive bike, this could be something that is either a lighter grade aluminum, potentially even some carbon fiber components, but we'll be looking at aluminum. I'm going to be excluding the pedal from the analysis. I'm going to be applying the load with some rigid body connectors. The reason I'm doing this is just because I'm not designing the pedal. The pedal could be a variety of things. It could be a pedal. It could also be a clip or a clip type shoe. I'm not a pedal designer. I'm designing this crank arm, so I'm focusing my attention on the crank arm and looking at the load being applied to that specifically. I will be applying the load at the center of the pedal, so I'm offsetting that load and where it's being applied to the center of the pedal. This will sort of take into account some of the bending that will occur and twisting as a result of where that load is being applied on the arm. Also, my stress ratio, I'm going to be just applying it in one direction and then unloading it. This is assuming as the pedal comes around the other side that most of my load will be transferred to the other foot as I'm going up a hill. There may be some compression depending on how this is set up, but in this case I'm assuming my stress ratio is 0 and I'm applying my load in one direction and then unloading it to 0. So look at results in a moment. I want to go ahead and jump into Nastran and CAD so that you can see what the setup looks like and some of those things I need to change. So remember, there's 4 steps to this. So I simplified the model. I basically just excluded that pedal there. It shows in transparent. This shows that it's in my assembly, but I've excluded it from my Nastran study. I've applied a mesh, pretty small size mesh. I've also added in some mesh controls around the location of the load as well as near where I'm going to be fixing my crank arm to the crank assembly. So this will help to get a better stress distribution and more accurate results in the areas where I expect to see an increase in stress. So for my study type, if I go ahead and look at this, there's all these different types that Nastran and CAD has available. I selected multi-axial fatigue here, and so then I can go ahead and start to apply all of my data necessary for this analysis. The nice thing about fatigue is that it runs a linear static analysis as well. So my results will actually give me fatigue results, but also my linear static analysis results. So I get both with the same analysis. So I'm applying my load here. I'm representing it with really just about 100 pound force. So I'm taking basically about half of the load that I would expect from an average size rider to be applying to this. Obviously, some of the load will be taken by the seat of the bike as well as the opposite pedal and some of the other materials involved in that. So I'm expecting about 100 pound force being applied from the center point of the pedal to this other side of my crank arm. I fixed it with rigid body connectors. This just allows me to transfer my load from here to there with a rigid element, assuming that I have this pedal matched up with that hole and bonded with a weld or with a screw to the bore of that hole. So I'm going to be applying this load. I will need to go ahead and set up my fatigue analysis with those things. So first things first, we'll go to my aluminum material and we'll edit. In here, I'm just going to go and leave all my values as they are, but I will change this fatigue. So under Analysis, Specific Data, I'll go to Fatigue. And in here is where I can enter in my SN data. So I take the SN data from the curve I showed earlier. So I pulled this from a mil-spec handbook that I use for my materials. I gather my data. I'll input in my ultimate, so basically where the stress value intercepts on that curve, the number of cycles where it intercepts, and then also the endurance limit, so what stress value occurs at that endurance limit. So for aluminum, I'm going to actually have the same B value, so the same slope of the line before and after the endurance limit is reached, because I'm assuming there's not going to be a huge change. And looking at that curve with all of these different curves for this aluminum material, the actual slope of the line doesn't change significantly after it reaches the endurance limit. As opposed to about a steel material, you may see sort of a flat line after you hit that, but in this case, I'm going to be fine using the same slopes before and after. So enter in your SN data. This is going to be best for high cycle fatigue, and that's what I'm looking at today. So I'll apply my SN data to my material specifically. Then I'll go to my fatigue setup. In here, I haven't changed any values. You'll notice the approach here is stress life or strain life. Strain life represents that EN data. Strain life is effective if you're looking at low cycle fatigue, so a really large load where you're expecting to see fatigue with a fewer number of cycles. In this case, I'm looking at, and I'm most concerned with high cycle fatigue. So once I get over about 200,000 cycles. The method by default will be von Mises, so it's using von Mises to calculate sort of the stress versus cycles, and that should line up with the curve that you select. So the curve I selected uses von Mises stress versus cycles. So the method should match the curve that you select. You can also use principal or shear if you're looking at compression or shear and fatigue using that method. So depending on the curve that you select, you may use one of these other methods, but typically von Mises is the most common. There's some other values here, such as threshold. So this is a percentage of amplitude threshold. I'm not going to change anything there. My event duration, if I will be applying an event that lasts a certain amount of time, so maybe the actual load isn't applied without time dependency, maybe it's applied slowly over 5 seconds or something, I can enter in an event duration, and it'll use that value for the overall cycle time. And then a time conversion factor, if I'm converting my event duration to any units besides seconds, I can add in a conversion factor there as well. Typically for a study like this, I'm not going to be using any type of event duration. I'm just going to assume a load will be applied and taken away sort of in a non-time dependent manner. So for my load, I will want to make sure that I apply this to match the stress ratio. So if I edit my load here, I have that 100-pound force load applied in the negative X direction here, so down onto that point. You'll notice this table for fatigue that shows up below my load. This is the load history table data. So if you go ahead and click this icon here, you can create a new table. So if I look at the table that I created, I'm doing this without any time dependency. So this is a dimensionless application. So I'm just going to be applying, basically showing how the load will be applied and taken away. So if I show my XY plot here, you'll see that load is just going to be applied at a maximum and then taken away, and this represents the stress ratio of 0. If I had a stress ratio of 1, I'd have to define it in the negative direction as well to represent the compression that would also be applied. You can also use the load skill factor versus time plot if you want to have a time-dependent load applied. So maybe your load is being applied slowly over 5 seconds and then taken away over 2 seconds. You can define a very specific load skill factor versus time table here if necessary. So I have my fatigue study set. I've defined my SN material data. I have defined my fatigue setup, and I've defined my time-dependent or load time history for my load that I'm applying here. I've also just fixed the inside bore here where I will be bonding this to the crank arm, so this will be fixed to that crank arm, so I'll be fixing that entire hole. And I'll be applying a load at the center of the pedal as I mentioned before. So the fatigue analysis does not take very long to run. I'm not going to run it right now, but it usually, with a simple part like this, it'll usually run within a matter of a couple of minutes. If you had a larger assembly, it may take longer than that, but it is very quick. It's going to run that linear static analysis and then go ahead and apply our SN curve data and look at what would happen as we approach 100,000 cycles and 1 million cycles, and at what point we would expect to see some failures. So for my results, first thing I can look at is von Mises. So if I just look at my von Mises stress here, I'll expect to see this arm under deformation start to bend down with the load, but also if I look at it from the top here, you'll see it start to twist a little bit as a result of the location of that load being applied. My maximum value is about 29,000 PSI. And if I zoom in, I can see that's generally along the inside edge of this bore on the back. So this is basically a slot cut out to cut some weight. I'm going to be seeing some maximum stress sort of in the transition from that to where I'm fixing it. So sort of at the extension of this slot along the edge. I'm also going to see some stress increase along the lower fillet of my crank arm near where it's being fixed as well. So in general, if I were to just look at this with linear static analysis, I'm only hitting 29,000 PSI, and the yield strength for my aluminum is about 40,000 PSI. So I'm below the yield strength of my material. I would assume that this isn't going to fail. I have a good cushion there and a good safety factor where I'm pretty comfortable with running this and sending it out. But if I'd like to see what I could expect as this is loaded over and over again, I'll need to look at my life results. So underneath results, I'll see fatigue results. And if I go ahead and load those up, and I filter to look at my solid life, I'll get a scale on the left-hand side with number of cycles, and then the plot defined on my actual part. So blue represents basically my largest number of cycles. Red would represent my basically minimum number of cycles before I see any failure. So I'll see sort of a distribution that looks a little bit different than my von Mises through here, where I'm expecting to see fatigue on the side and top of my arm. If I look on the other side for where my minimum value is, it's right at this fillet here at the end of the slot, furthest away from where the load is being applied, where I'm going to be seeing a significant amount of moment as well as twisting and the stress resulting in this area. So it's a similar location to where I saw some stress increase in my von Mises, but now instead of getting just the stress value, I get the minimum number of cycles before I may see some fatigue occur. So I can expect to see failure and damage in this area after about 7 million, almost 8 million cycles. So that seems like a lot, and the thing with fatigue analysis is you always have to put it in perspective of how your design is going to be used in real life. So 8 million cycles, what does that really mean in relation to riding a bicycle? So let's go ahead and review the results here. So I don't design bicycle crank arms, but in this case, let's just say that our design criteria is that this will last 10,000 miles under this maximum load condition. So it's not always going to be loaded at this high value. This is sort of looking at the worst case scenario. But let's say we want to make sure that it at least would last 10,000 miles if someone did load it in this fashion. So our value that we got was about 7 million, almost 8 million cycles before we would expect failure. So sort of doing some math, looking at 1 mile, that's about 63,000 inches, and one wheel rotation represents about 65 gear inches. This will change depending on what gear you are in, but I'm assuming sort of a middle gear. for this analysis. So I would be getting about 65 gear inches per rotation. So each wheel rotation represents 1 cycle on a bicycle. So doing more math, if I were to take my inches in a mile and divide it by gear inches, I get about 975 cycles. And so I would expect that this crank arm under this load condition would last me about a little over 8,000 miles before I would expect to see failure. And failure in this case represents sort of seeing some damage as a result of fatigue, and it's only going to occur in those areas of my model where I saw sort of that concentration, where I saw that red contour. And so in this case, I would probably assume that maybe I could do some further design optimization. If I want to reach that design criteria of this lasting 10,000 miles under this load condition, it's likely that I'll want to maybe reduce the size of that slot or change my material so that I get a longer life out of this crank arm. And 10,000 miles is quite a bit, considering this load case being like a worst case scenario. This would be almost as if basically our rider were to be climbing hills constantly and they happen to weigh a significant amount. That's what would just create this load case. So that's pretty unlikely. So this value of about 7 million, 8 million cycles is pretty good, but I could certainly do a little bit more improvement to try to reach that 10,000 mile design criteria. So just sort of to recap things, you know, linear static analysis, if we were to just run that, we do get our value for our maximum load condition, and we're showing a value of that 29,000 PSI on this crank arm should be just fine. We're not expecting to see any yielding in this load situation, but Nastran CAD gives us the ability to not only look at linear static, but also look at a dynamic time-dependent load and its effect on our component, and we can look at how many cycles we'd expect to see before we expect any failure to occur. So that's pretty much going to wrap up everything I wanted to talk to you about on fatigue. I appreciate your time. Hopefully that gave you a good overview and you have some information to take back and either apply to some fatigue analysis you'd like to run, or if you are interested, maybe this piqued your interest in Nastran CAD and you want to give it a closer look. So appreciate your time, and if you have any questions, go ahead and reach out to Cassie or send a chat, and I think we can then get those answered.
Thank you very much, Ed. Very informative. It looks like we had 1 or 2 questions coming through that Cassie can help us with.